the Sustainability Management Master's Program, you are answering one simple question. Do you care about your future generation? If you care about your kids, their grandkids, then you care about sustainability. And a sustainability manager is someone who has the tools to make people understand how they can contribute towards developing a sustainable world. We have both part-time and full-time students. Our curriculum is 30 hours. Instead of thesis, we have a research project course and a seminar course which provides them with the kind of research background they will need to be successful in their job. At the same time, sustainability is not always everything about environment. It also relates to the business. They will take a sustainable business strategies course. They will take a project management course. Most of these courses are going to be taught by industry people, the people who are doing sustainability on a daily basis as a part of their job. Any organization that has a large number of employees and has a physical infrastructure, they will have to have a sustainability office. If you have the passion to develop and maintain a sustainable world, come to us and we will help you shape your passion into a career which will create an impact.
Yeah, thanks everyone. Joe apologizes. I wish Joe was here. He was, Joe and I have known each other for like 25, 30 years, and he's a real pioneer in wastewater treatment, industrial wastewater treatment. He actually wrote a book with somebody, if you're a wastewater engineer, Wesley Eckenfelder. So Wesley Eckenfelder was like a pioneer in industrial wastewater treatment. And Joe actually wrote a book with him. Unfortunately, Wes had passed away while he was finishing the book. So, Joe's a kind of, we call him a legend, in the business. And pinch hitting is John Persigo from my office. He was kind enough to sort of join me and sort of help me out here when I fumble on what Geosyntec does. So since I've only been here for three and a half months. So one thing I learned, I went to a pharmaceutical conference, and he said I have 35 plus years experience. So talking to the young ladies out there who eventually, as they grow in their careers, ladies use plus 30 years experience, guys use plus 35. So that's about as far as the experience level goes with people, okay? So I wanted everybody to know that. That was kind of an interesting factoid I found out. So my topic today is on pharmaceutical wastewaters, treatment trends, and what are the key issues. And a lot of this information is basically my knowledge of the pharmaceutical industry. As Dibs mentioned, I actually started talking about this issue back in like the late 90s with one of our large pharmaceutical clients. And it's basically, over time, it's grown into a real, sometimes there's a lot of activity on it, sometimes there's not. So I wanted to basically talk today about what's going on in the industry. So the outline on this, I just want to give you a background on what APIs are, active pharmaceutical ingredients, and talk about the background. Boy, I gotta look at my, put on my glasses here. So basically, the other thing I want to talk about is how to predict how APIs enter the environment from pharmaceutical processes. And then I want to talk about source control options in the pharmaceutical industry. A lot of people talk about end of pipe, but what's really important in pharmaceutical industry is we focus at the source. And then I'm going to talk about some other treatment technologies and some case studies of what Joe has done primarily with pharmaceutical clients. And then I'll just talk briefly about what some of the takeaway points are. So some people know about pharmaceuticals and the environment. They may call them microconstituents. So if you look up EPA's website, they talk about microconstituents. And essentially, it's a inorganic, organic chemical, very, very small concentrations, but they have potential effects on human receptors and ecological receptors. And the primary thing that I focus on in pharmaceuticals are pharmaceutical drugs and synthetic and naturally occurring hormones. And there's other microconstituents out there. We are talking about flame retardants. Another area is the perfluorinated type of compounds, the PFAS, the PFAS. So there's a lot of focus on these chemicals because they bioaccumulate in the food chain, and they have very low cleanup standards. Nanoparticles are a really important area because they're making a lot of using processes with nanoparticle metals, and so they can get into wastewater streams. And how do you remove those particular nanoparticles? So it's you know, these are sort of the list of microconstituents. My focus is on drugs, pharmaceutical drugs. So what is with active pharmaceutical ingredients, what is their route to the ecosystem? Well, 5%, less than 5% come from manufacturing facilities, and not a lot. Basically 90% of it comes from humans. We metabolize to take prescription meds, and we excrete them. You know, we don't break them down. And then some are, about 10% come from unused dosages prescribed to patients. Unfortunately, some patients put them in the garbage. The garbage is landfilled. They ultimately get into the leachate systems. And now there's a huge effort with companies like Waste Management, Republic Services that run landfills. The municipalities won't accept their leachate anymore. So the only way they can do this is actually to run their leachate through evaporators, and because municipalities won't take they won't take this leachate because it has pharmaceuticals, but it also has some of these other compounds in it too. So and I think what's important, the takeaway on this, and what I feel, is that what's the biggest problem here in the United States with regards to pharmaceuticals, social wise? Does anybody know? So it's the opioids. So it's basically people taking opioids and you know, sort of like ODing on the streets and stuff. Well, that's why it's important for you, if you have unused pharmaceuticals, that's why it's not just don't toss them in the garbage, put them in a secured container like you see at a drugstore. So APIs in the environment, they basically can be classified in 3 areas: toxic chemicals, really, and what I call cytotoxic chemicals, which are really, some of your anti-cancer drugs. Basically, at very low dosages, they're extremely toxic to the human body. And endocrine disruptors, hormones, and that's an issue because you hear about feminization of fish in the aquatic streams, things like that. And then the other one is antibiotics. And antibiotics are, I think, one of the real emerging issues coming up these days. Because if you look at any of this World Health Organization stuff, there's a lot of talk about antimicrobial resistance. And antibiotics are so much in our ecosystem that basically there's so many different bacteria now that are becoming resistant. So there's like tuberculosis, there's resistant strains of tuberculosis now. And it's an issue. It's a real issue. And pharmaceutical companies now, that's their biggest focus is antibiotics. How to treat antibiotics to make sure they don't go into the environment. So why focus? Why is the focus by large pharma? And a lot of our clients are large pharma. The big companies like Bayer, Sanofi, Pfizer, Johnson & Johnson. Why is there a focus by these large pharmaceutical companies on this issue? That's because they use contract manufacturers throughout the world. Pharmaceutical industry has become very competitive. Okay, it's not like it was like 15 years ago when they were making tons of money. Okay, it's become very competitive. And the problem is a lot of these drugs now have gone off patent, and they go off patent, they become generic. There's no big blockbusters out there. Everybody's trying to discover the next perfect molecule. So what happens is they're still making the medicines that treat depression, treat cardiac issues, and what they do is they depend on contract manufacturers quite a bit. And these companies, they make the capsules, they make the tablets, they make the liquids, they do everything. They synthesize the drug product. So with these companies, there's not a lot of control with these contract manufacturers and how they treat their waste, how they make their processes. So it's really important that the big pharma companies, now we're starting to look at these companies and say, okay, what are you discharging? How are you discharging wastewater into the POTW, and does it have a lot of pharmaceutical in it? So there's a big focus now with most of the pharmaceutical companies on these contract manufacturers. So a lot of people have seen APIs in the headlines, you know, whether it's feminization of fish. There's been a lot of papers, scientific papers that have come out. There's actually, China now has a lot of information out there. There's a lot of Chinese research going on. And what happens with these issues, when they hit the journals or they hit the you know, the periodicals, it's like, hey, we found part per million concentrations of a particular antidepressant in the receiving water. And well, okay, so whose antidepressant is it? Well, is it Pfizer's? Is it Johnson & Johnson's? And it hits the press, and then people, you know, the pharmaceutical companies do not like it. So this is, again, one of the focus. What's interesting, I wanted to show this. This is a kind of interesting graph. And it basically talks about the different pharmaceuticals, the types of pharmaceuticals that are basically consumed by humans. And it's given in basically daily dosage per day per 1,000 inhabitants. And the brackets I show there are some of the ones of concern. That's the hormones, the antibiotics, and the anti-cancer drugs. And what's sort of interesting about this, and so you got to maybe sort of understand this, those products, fortunately, are given in very low dosages. So there's not this huge mass that goes out into the environment. So that's a good thing. So cytotoxic compounds, anti-cancer drugs, very low dosages, okay? And these compounds, I mean, the cytotoxic compounds, I went to a facility in a little container of API, active pharmaceutical ingredient. You had to wear level A protection because you don't want to be near this stuff. A little canister, $50,000 for that drug product. It was amazing. I was shocked at how much it costs. And then they take that and they formulate it into liquids and things like that. But fortunately for hormones, for anti-cancer drugs, for antibiotics, it's not a really big bandwidth. The bigger consumers are like your cardiac drugs and things like that. So we talked about cytotoxic APIs, and again, these are just basically high potency active pharmaceutical ingredients, and they're extremely they're very active from a pharmacology perspective, but they're also they can be extremely toxic to humans. And they have very strict requirements as far as the health and safety of people who manufacture these compounds. And again, fortunately, they're the most extremely toxic compound, but they're at the lowest dosage. So you don't really see cytotoxics that much in the environment. If you do, you see them in really like part per trillion, low part per trillion concentrations. And the normal way to handle these compounds is, as mentioned, level A PPE. You have to dress up in moon suits basically to handle this stuff. These are specially designed systems that basically contain the air. So they have special air handling units. They have isolation locks. When an operator comes out, he's decontaminated with hypochlorite or some solution. They go through, like typical hazardous waste site, you go through a decontamination area. And the fortunate thing about cytotoxics is because of how toxic they are, they're very well handled in the pharmaceutical industry. We have special treatment processes that handle this stuff. They're acidified, they're hit with caustic, or they're chlorinated. And that's how, depending on the molecule, the anti-cancer drug they treat any kind of waters that are generated from that formulation. So this ONeil report was sort of a genesis on a lot of the antibiotic-resistant organisms. It was commissioned by the UK government, but basically said, we got to do something about this. This is really important. This is a major issue, understanding antibiotic resistance and how its impact to basically our human health. Okay, and this was a report that was commissioned. And so in the United States, there's greater than 25,000 deaths a year due to just basically the fact that we don't have an antibiotic that is basically can handle that particular infection. And so it's become an extremely important issue with the pharmaceutical industry. I can tell you that all the major pharmaceutical companies, all the major heads of the environmental health safety divisions are focused on this issue. This is a major issue. And one of the things that is kind of interesting is, well, there's been a lack of discovery of new types of antibiotics. So that's also not good either. So the combination of having this issue come up and the fact that we're not discovering any new types of antibiotics, it's an issue in the world. And so this just shows a map of basically pretty much every country in the world that has identified an issue with a resistant strain of tuberculosis. So it's a big issue, and I can't say enough about it. It's just essentially it's really the pharmaceutical industry is very focused on this because we got to have antibiotics when we're in a hospital and we have to fight certain disease, certain infections. It's extremely important. So again, it's become a very big issue. Right now there's not a big pipeline of new antibiotics out there, so it's a real concern. Everyone's talking about this. And we talked about antimicrobial resistance, and I'm not going to talk real specific about this, but this is like just a slide that talks about the fate and transport of the compounds in the environment. And what everybody thinks, like in wastewater treatment, you're biologically treating waste. Oh, you may break down the molecule and you might get some removal. Well, it's great. It doesn't go out in the water, but it goes out in the sludge. So what do you do with the sludges? You put a lot of sludges go to land. So it gets into the food chain, and that's why there's it's sort of an endless cycle. So I want to talk about how to remove APIs, active pharmaceutical ingredients, and I want to talk about how to predict them and how to prevent them. I'm going to talk a little bit about pharmaceutical processes. So what we do in the pharmaceutical industry is what we do is an impact assessment. You evaluate the process, the pharmaceutical process, and you determine how it gets into the water, into the wastewater system. So we end up generating estimates. Some estimates are based on batch records. We can, we can really determine what we call basically unaccountable losses are, because the pharmaceutical industry is so it's so driven by batch records. Everybody knows what the yield is. So I could say, I added 70 kilograms of this active ingredient and I got 99.92% yield, because I know what went into my product. I know what went into my samples. So it's a very well regulated process, but requires a lot of data interpretation and professional judgment. People who know the processes. And so what we try to do, the first step is try to predict the environmental concentration, or the PEC. And the next thing we have, the other piece of information we have, is the predicted no effect concentration, the PNEC. And I'll talk a little bit about that. There's ways to calculate the PNEC value. And then what we do is just take the PEC over the PNEC and essentially develop an RQ, risk quotient. Anything over 1 requires appropriate action. So it's a risk assessment, it's a desktop risk assessment for looking at pharmaceutical processes. So in calculating the PECs is how much goes into the environment. And essentially it's just basically it's a mass balance, understanding what the flow is and understanding what the concentration is. You know how much mass goes into the environment. So, and then sometimes what we try to do in predicted environmental concentrations, we want to understand what its effect is, you know, accounting for dilution, like receiving streams, when the wastewater goes into a receiving stream. And we also want to understand if there's any reduction that's occurred at the facility. And so we need to understand treatability, we need to understand dilution factors. So at an operating facility, you have what you're making, say, a pharmaceutical liquid, you're putting the active ingredient in, then potentially you dispose of some of that liquid down the sewer while you can figure out what the mass is. That's the sort of the loss that you may not want to see go down the sewer. And so we call that the unaccountable loss. A lot of the loss occurs, you have systems like dust collection systems, so you're using dust collectors and for engineering controls. That stuff goes into filters and ultimately incinerated, because we incinerate all our APIs. We don't put them into landfills. Okay, so everything in the pharmaceutical industry is incinerated. And so looking at the operating facility, the other aspect is understanding what is happening at the wastewater treatment plant, at the pharmaceutical facility, if they have a wastewater treatment system, or understanding what's going on at the POTW. And then ultimately we want to understand how it hits the receiving stream. So we want to understand, we're focused really on what is the predicted environmental concentration in the receiving stream. That's the most important number we need to calculate. And then we take that and we want to know what the PNEC is. So there's a couple ways to figure out PNECs. One is looking at your aquatic data, and the more the data, the better. And what we do is look at the lowest no effect concentration of that particular species, whether it's Daphne or green algae, things like that. And sometimes those are available data from the supplier, but you can take that information and then calculate a PNEC by taking the lowest, you'll take the lowest concentration that's recorded and divide it by an assessment factor. So in this case, we divided it by 10 because of the fact that we had 3 data points. So that's the PNEC, the way you calculate it. And in this case, it's relatively low. It's 0.014 milligrams per liter. So that's a predicted no effect concentration. So there's also published values of PNECs. The Antimicrobial Resistant Alliance has their published PNECs for all antibiotics, pretty much everything. Also, there's a lot of good scientific journals out there that have PNEC values that are published. And then there's basically in Temple, there's the Water Environment Technology Center, and they do a lot of this type of research, understanding what the PNECs are. So you divide the predicted environmental concentration into you divide the PNEC into the predicted environmental concentration, come up with a risk quotient. Again, anything greater than 1, you got to do something. So let's talk a little bit about the processes in pharmaceuticals. I come from the organic synthesis area, so basically large, batch reactors, different types of chemical processes, vacuum distillation, heating, centrifuging, filtration, and generating the molecule through organic synthesis. There's fermentation processes, but in pharmaceuticals, there's also like oral solid dosage facilities, guys who make the pills. You take the active ingredient, you mix it with some incipient, you put it in a capsule or make a tablet, and that's your oral solid dosage. Then liquids. So liquids are injectable bags, things you hang off of IVs. Liquids are ampules that you basically stick syringes in and pull out a certain dose of whatever that liquid is. Again, it's a very, very sterile environment. Anything when you're formulating drugs is a very sterile environment, but liquids are it's an extremely tight process. And then there's also the other thing I wanted to talk about was just clean in place systems. A lot of this equipment needs to be cleaned at some point in time after a batch is done. A lot of very strict validation processes to clean, and they use these clean in place systems, and they generate the wastewater. You know, they have alkaline, acidic type cleaners, and that's how they clean their equipment. So again, basically you want to reduce the API that goes to wastewater, so you want to use dry cleaning practices as much as practical. You want to minimize wet cleaning processes, and you want to eliminate the discharge to sewers. So you want to do these things, and you want to see if your RQ is less than 1. If it's not less than 1, you need to go to level 2, which I'll talk about. That's point of generation treatment. So these are dry cleaning processes. So does anybody know what this is at all? That piece of equipment? If you look at the sort of the dies around this, it's a circular thing, but there's all these little dies. Does anybody have any thoughts on that? Yeah, exactly. So that makes tablets. That's a very, very poor leaky system. So you don't take a hose and flush that down the sewer. The objective is you want to use dry cleaning processes. So here's a picture of a guy using not a central vac, but a localized vac system, and he's sucking out any powders out of the equipment. So in tablet formulation, oral solid dosage, everybody uses vacuum systems. If you go into a pharmaceutical suite, every pharmaceutical suite has a central vac, hookup. So you want to minimize wet cleaning practices. So again, you don't want to be, taking a fire hose and hosing down all the equipment and putting it to the drain. The objective is to first suck up this material as much as possible and incinerate the powder that you collect, and then you can use your wet cleaning process. So the other thing you want to do is eliminate direct discharges to the sewer. So this is a liquid formulation suite to the right. It's immaculate system. It's epoxy floors. There's no floor drains. The idea is to clean these tanks using a clean in place system, which is to the left. And what we want to do is capture that water after cleaning in place and treat that water specially. We don't want to just, again, discharge that to the sewer. So the second level of treatment is to collect wastewaters at point of generation. Okay, and basically we have clients that have, they clean their equipment like first, second rinses. It has very, very, very minuscule concentrations of API, but they don't want to send it to the POTW. They want to collect it. They take it off for off-site incineration. But there's other treatment steps. You can do alkaline treatment. You can do advanced oxidation. A technology we're looking at is electrochemical advanced oxidation. And what's actually it's quite a bit in India because the prices of energy is evaporation, zero liquid discharge technologies. I don't know how, I've heard zero liquid discharge is used more prevalently in India. I don't know if it's, if that's more of a, urban legend or, it's because there's also high concentrations of pharmaceuticals in surface waters in India. And then again, off-site incineration. This is an advanced oxidation system, which basically takes small volumes of wastewater, collects it. They run it through basically an hydrogen peroxide ozone process. It's called HYPOX. So again, we want to try to make sure after you do this, let's make sure that the impact to the environment, the RQ is less than 1. If it's not less than 1, we have to go to level 3, which is then the pipe. But I want to show you another technology that's sort of we're looking at now. It's just a simple evaporation process. You're taking those wastewaters that have those concentrations in it. Again, we're not talking to high volume, and you're evaporating, just generating a steam plume and basically you end up with a brine at the end of the process. So this is something that we're looking at right now for clients. It's a very cheap way to treat water. It's basically with the price of natural gas, it's somewhere between like 8 cents to 8 cents to maybe as high as 15 cents, but mostly more down like less than 10 cents a gallon. And the other thing that's interesting about it is that you know, it's much cheaper than off-site incineration. It's you know, you pay a buck a gallon or even $1.50 a gallon to incinerate water. So I want to talk at high level what some of the treatment technologies, what's working out there. So conventional activated sludge. Everybody likes conventional activated sludge. I've put a lot of these systems in at pharmaceutical facilities over my years. It's great to remove the API out of the water, but you also want to understand what's in the sludge. Sequencing batch reactors, another aerobic biological process. When I first started my career, I was the first one to put in an SBR in Puerto Rico. That was the first SBR that was ever constructed in Puerto Rico. It worked great because it just consumed alcohols. It was like alcohol was jelly beans to the bugs. I mean, it was like, and we generated sludge, but it was a great system, and it really saved a lot of money for the company. And when it was funny, when I went back after, you know, the pharmaceutical industry changes, like, you know, there's owners, different owners. Oh, it used to be owned by Pfizer, now it's owned by Johnson & Johnson, now it's owned by Pharmacy. You know, so it's like got this like a crazy, you know, sort of history behind it. And so I got sent down to this plant because they knew I put the wastewater treatment system in. So I go down there and I said, they're running the wastewater treatment system. And I said, well, what's your loading rate? They go, oh, it's about 5 pounds a day. And the thing was designed for, I don't know, 2,000 pounds a day. I go, you're kidding me. You're running this system? So what I did was I took all the alcohol, basically, that was being incinerated by Veolia at $1.50 a gallon and just fed it to the biological system. So it worked great. So moving bed reactors, another technology, and another technology are basically membrane bioreactors. That's sort of like some of the new pharmaceutical plants are putting these systems in. And these are generally at large API plants that generate or synthesize chemical, organic APIs. They don't put these systems in at formulation facilities because they have a very weak load. There's not much weight, there's not much high strength wastewater coming from a formulation facility. Ozone works great. We've got systems in with ozone, and it works well. Especially it works well on certain, a lot of pharmaceuticals, on hormones, antibiotics. It cleaves a lot of critical rings, and so ozone treatment is a very prevalent process in wastewater at pharmaceutical facilities. We did an evaluation of Chemox treatment processes, looking at UV, hydrogen peroxide, catalyzed UV, hydrogen peroxide, different chemical oxidation processes, and the compound reduction that we get with APIs, reducing the API in the water is like over 99%. The problem is with these processes, if you have a lot of other organics in there, like alcohols and things like that, it's a much higher cost. So generally, you try to use this more at the end of pipe, or not end of pipe, but more of a polishing process. Case study in Ireland and France, we looked at 4 plants. Each plant had 1 or 2 APIs. We were concerned about the fate of the API leaving the treatment system. We wanted to understand, how the removal correlated to the treatment plant design. And so this was a study that was done. We looked at the plants. We showed what the mass balance was. Again, it was, for some processes, it worked great and there wasn't much detected in the effluent. And then in some processes, a very poor treatment. So it depends on the molecule that you're trying to break down and the type of biological treatment system. in this situation, you can see we have what the sludge age is and the temperatures of the biological treatment process. So, looked at a site in Ireland. We had some different types of APIs. We had a mixture of hormones, various synthetic hormones, hormones that come from extraction processes. Real interesting concept. Be curious to understand if anyone understands how a particular hormone is basically processed. How do you get a hormone? Does anybody know? So there's a hormone out there for it's mostly women take hormones, obviously, and so it's called Premarin. And people understand, well, what does Premarin mean? Well, you know what Premarin? Okay, where does it come from?
It is pregnant mare urine.
Yes, it is. Very good. Are you from Canada?
I worked in pharmaceuticals.
Oh, okay. Okay. Well, actually, I've been to this facility, and what's interesting is it's a very interesting process. The mare gets pregnant at a certain time of the year. It goes through its gestation period, which is basically less than a year, I think, and then when it gets toward the end of before they have the mare, they basically collect their urine because that has the highest concentration of estrogen in the urine, and then they go through an extraction process. So that's how they make this estrogen. Does anybody know? Has anybody heard of heparin before? You know what heparin is? So it's a blood thinner. Do you know how you get heparin? You basically take intestines of pigs, and it's extracted in alcohol, and you extract the chemical out of the I can't even say it, the mucosa of the intestines. So that's how you get heparin. So this young lady's like, ooh. Yeah, that's right. And what you're supposed to do is you're supposed to endorse eating bacon and sausages in Iowa because that's where the intestines come from. So I'm just telling you a little bit of little factoid there. So one of the things we did, we looked at a bunch of different processes, higher sludge age, looking at different types of biological treatment. So this was an evaluation we did with different alternatives. And so we basically ended up sort of looking at getting it down to, a membrane bioreactor to take out the high strength materials, the organics, followed by an ozone oxidation system. And it really, again, did a great job. The combination of both biological followed by ozone polishing is really worked out well. This was for us, it was a proven technology. We convinced the client to actually try, to implement it, and we ended up, there's a schematic of the process, but we put it into a facility in Europe. So this is the treatment system. They have an oxygen tank there for basically, this is in UK. They have an oxygen tank there for the ozone, to generate the ozone. So instead of using air, they put in pure oxygen. Here's basically the ozonators at the site, and we did a bunch of sampling in this process. So we did performance verification, and what we did in this facility, we looked. If you see that black line, basically the APIs dropped down to nothing. So there was still COD, and I don't know what the other parameter is, but the APIs were destroyed with ozone polishing. And then we also looked at, we sort of did an estrogen screen at this site because it had hormones, and again, the hormone concentrations were significantly reduced. So kind of my takeaway on this, I wanted to really kind of drive some points home with you guys before you leave. The current driver in the pharmaceutical industry is antimicrobial resistance and to reduce the amount of antibiotics that get to the environment. So we're working with some clients now looking at specific treatment processes. It's interesting, some of these pharmaceutical facilities that basically make antibiotics are done mostly with fermentation. And the fermentation process is larger volumes. They end up generating larger amounts of waste, liquid waste. And some biological treatment systems work really well on certain antibiotics, certain molecules, and sometimes they don't break it down. So we're looking at sort of like some bench scale work right now where we're looking at increasing the temperature of the wastewater and then hitting it with chlorine basically. So there's another thing we're looking at now. We're looking at electrochemical advanced oxidation processes. The pharmaceutical industry is predicting now at contract manufacturers, this is actively ongoing and there's a number of people doing this. They're predicting the risk quotient at these facilities because they don't have control of the production processes, so they're trying to get as much information about how do you guys put, how do you treat your waste? How do you treat your wastewater that's generated from a liquid formulation facility, a tablet manufacturing facility, organic synthesis plant? How are you collecting that and treating that particular wastewater that may contain the APIs? Anything that is greater than 1, go back to the process and try to make it better, because that's better. Good management practices, using dry cleaning, minimizing wet cleaning processes. That's level 1. If it's still greater than 1, you look at point of discharge, okay? Because again, you're just creating a tier, and you're trying to go from least expensive to most expensive processes. And point of discharge treatment is extremely successful. If you think about it, if you got liquids and you just evaporate them, that's the easiest thing to do. And just create a brine, and that brine you can dispose of off-site. That's what's incinerated. So you minimize the amount of material going off-site for incineration. Evaporation's a good technology. Hypox systems are an excellent process. Again, that's hydrogen peroxide and ozone. And then if it's still an issue, go to level 3, which is end of pipe. So we found that biological treatment, advanced oxidation, was really a proven sort of process train that worked very well. We used biological treatment to take care of the majority of the organics and then polish it with advanced oxidation. So ozone and other oxidation processes have been, again, used very well in the polishing step. And we found that in that analysis estrogen compounds and APIs, we got over 99% removal. We look at treatability studies, process modeling tools, and we're working with clients today in coming up with different design criteria to come up with solutions if you have to go to end of pipe. And again, carbon absorption, alkalization, electrochemical processes, thermal evaporation, they're all decent processes to evaluate. And basically, again, the best way to handle this issue is really how to manage the production process, what to do when you make a tablet, when you make a liquid, and understand you don't want it to go to the sewer. That's the bottom line. So I think that's it. So any questions?